Hi everyone, it's now 2 o'clock. I think we can start. So for those of you who are regular attendees to these mini schools, you'll perhaps recognize that I'm not Francesco Fraccioni. So for those of you who don't know me, I'm Dr. Graham Pleasance. I'm a postdoc in the Quantum at Sun group here at Stellenbosch University. And today we have the second part of the mini school on exploring the frontiers of electronic structure. Which will again be delivered by Shane McFarthing. So yeah, I think without any further ado, I can hand over to Shane, and I can just say that if you have any questions during the talk, then just please feel free to make use of the Q&A facility, and then we'll have time for questions at the end. Okay, so yeah, over to Shane.
Great, thanks very much, Graham. Yeah, so let me just share my screen and we can start. Okay, great. Yeah, so this is the second lecture in our mini school about electronic structure. And to begin, I'd just like to go through a recap of what we did in the first lecture. So in the first lecture, we gave an introduction into the electronic structure problem. We kind of introduced chemical systems and their constituent parts with wanting to describe the motion of electrons and how we use orbital functions to describe the probability of electrons being found in certain regions of the space around the nuclei. And then we posed the problem of trying to describe the motion of these electrons to give us states of interest. And we do this by formulating the Schrödinger equation for the electronic system. So what we know is that the solutions to the Schrödinger equation give us these states of interest that we want to be able to find. And the reason why we want to do this is that those states are really useful for performing further chemical study to research properties like the reactivity of certain electronic systems and their states, things like spectroscopy, so the light emission and absorption, which is useful for industrial applications, like things like OLED display manufacturing, and then also other things like the conductivity of materials and stuff like that. So we know that we are interested in this because it has a lot of relevant applications that can be useful in industry and also in theoretical research. And that the reason why we do these simulations on the computer is that the normal laboratory research takes a lot of time and it's quite costly. And if we can speed up this sort of research pipeline in any way using computer hardware, it'll be really beneficial for us. And what we know is that we can use these computer algorithms in computational chemistry to obtain solutions that are usually quite satisfactory and at least reducing some of the work that needs to be done in the lab. So in today's lecture, we're going to be covering some of the classical methods for solving the Schrödinger equation. So in lecture 3, we talk about how we use quantum computing to perform this, to solve this problem for the application. But right now, we just start off with some of the more traditional methods that have been used on classical computing devices. And really, these are tried and true methods that are really widely spread. Their use is widespread in the industry. So the contents of the lecture is essentially going to cover 4 different methods for solving the electronic structure problem. And the first one is going to be the full configuration interaction method. And this method forms the exact solution of the electronic structure problem. And then we move into the Hartree-Fock approximation. And the reason we do this is that we need to try to reduce some of the computational overhead of using the full CI for reasons that we'll get into as we start the lecture. After that, we take a look at another really well-known approximation that's a bit of a higher level theory that gives better solutions in Hartree-Fock, which is the couple cluster approximation. And then lastly, we go into selected configuration interaction, which is a variation of the full CI method that also tries to reduce some of the computational cost. And in each of these sections, we're going to kind of introduce the method, explain how it works, at a bit of a surface level, and then we're going to give some examples of how you can create like Python scripts that would allow you to run these methods for specific chemical systems. So to start off with, we're going to take a look at the full configuration interaction method. So as I mentioned earlier, we're trying to solve the Schrödinger equation because the solutions of that equation form the description of the states that we're interested in. And you might wonder, well, can we solve this equation exactly? And you can do that if you use an exact diagonalization of the Hamiltonian. So we said that the Hamiltonian for a chemical system is the description of the total energy of that system. And what we can do is we can formulate a matrix from the Hamiltonian where the elements in the matrix determine the behavior of the Hamiltonian on specific electronic states in the system. And once we form that matrix, we can perform a diagonalization exactly. And what that does is it gives us the eigenvalues and eigenstates of the Hamiltonian, and those form the solutions of the Schrödinger equation that we were interested in from the beginning. So by doing this method or applying this method, we can get the exact solutions, but obviously the issue is that there's a lot of computational cost in performing the exact diagonalization of this matrix. So the number of configurations that we have in the system, so like the number of possible states that we're trying to consider, scales exponentially with both the number of electrons and the number of orbitals. Because if you try to think about the possible states in the system, if we have like k orbitals and we have n electrons, then we have possible number of configurations of k choose n. Because what we're looking at are all the possible ways where the electrons in the system can occupy the different orbitals that are available. And that scales exponentially, and the dimension of the matrix that we're concerned with also therefore scales exponentially. So we have quite a problem with trying to use this method for systems that are larger. And if you try to visualize how the wave function that is output by the full CI method looks, it's a linear combination of every possible valid electronic state of the system, and the coefficients in that wave function have all been exactly set in the diagonalization process. So we know it gives us the exact answer, but like I said, it has exponential scaling, and that scaling is linked to both the number of electrons and the number of orbitals, which is unfortunate because what we end up in a bit of a deadlock where this methodology can't really be applied to systems that have a meaningful number of orbitals and a meaningful number of electrons. So earlier I mentioned that the reason why we're interested in the electronic structure problem is because it can have a lot of relevant applications for like industrial use cases where we're trying to make money, we're trying to further material study or create new substances. And these are typically quite complex systems with large numbers of electrons and orbitals. And a system of that size is not feasible to solve using the exact method. And though there have been improvements in different areas, like different parts of the algorithm, for example, trying to make the diagonalization process more efficient through the use of methods like the Davidson algorithm, which reduce the computational complexity of the diagonalization, and also other exploits like trying to leverage the fact that the Hamiltonian is mostly sparse, where a lot of the entries are zero. We still can't get around the fact that this method is not really feasible or practical for large systems. So what we have to take a look at then are what are some other alternative methods that we can use to solve the equation that don't have the same cost, because we're trying to solve the equation and we only have access to like a theoretically limited hardware, so we can't use really expensive methodologies for trying to solve really complex systems, because that's what we're trying to do. Usually, if you're doing an application, you have a certain method. You'll test out the method initially on a smaller, simple system to validate the behavior of that. But the goal is always to go to more complex systems because that's where the reward is. So what we try to do is to do a bit of a trade-off where we reduce the computational cost by sacrificing some accuracy in our method. So the first method that we're going to take a look at is the Hartree-Fock approximation, which is really widely used in computational chemistry. So the first thing that we're going to take a look at is exactly what this is. And if you remember from the previous lecture, when we're talking about the electronic structure problem, it's a many electron problem. So we're trying to consider many electrons in the system moving around, interacting with each other and being correlated due to repulsion forces between them. And this is what makes the problem so difficult to solve, is we're trying to consider all of the motion of all of these different electrons at the same time and the forces and interactions between them. But what the Hartree-Fock approximation does is that instead of trying to consider the interaction between all of the electrons at the same time when they're moving around. So let's say we pick a specific electron I, and that's moving around the area around the nucleus. And we're trying to now take into account the correlation between that electron and every other electron in the system. It's quite difficult to do. So what the Hartree-Fock approximation does is it says, in fact, we'll just treat the general repulsion of all the other electrons as an average. And when we solve the equation, we'll take into account that average force on the electron that we're considering. So what it does is reduces the many electron Schrödinger equation to a set of one electron equations, where we have all the different interactions in the electrons represented by a mean field, or just an average electrostatic field that's created by all the other electrons. So when we look at exactly how you use this method, it's broken down into how do we define the wave function, what are the equations that we're trying to solve, and how are those defined in this mean field approximation. So the first thing we'll start off by taking a look at is the wave function form itself. So in the last lecture, when we defined how the wave function looks for the electronic structure problem, we said that it has to be an anti-symmetric wave function, and we made it Slater determinant, where it's a state that depends on the state of all the different orbital functions, which are the spin orbitals. And the simplest possible anti-symmetric wave function that you can have is the wave function of a single determinant only. So in the Hartree-Fock approximation, we simply consider a wave function of only one Slater determinant. And what we do in that Slater determinant for Hartree-Fock is that we set it so that all of the lowest energy orbitals are occupied by the electrons. So if we have n electrons, what we'll do is we'll occupy the orbitals starting from the lowest energy until we run out of electrons, and that will form the wave function that we have. So let's say we have let's say like a Slater determinant. We have 5 orbitals and we have 3 electrons. The way that these determinants can be visualized is as binary strings, and the Hartree-Fock state specifically would be the state where the first 3 positions are 1s and then the last 2 are 0s. So we just populate the lowest orbitals first. And that gives us the wave function. And then what we know is that we get the energy as the expectation value of the Hamiltonian with respect to the wave function itself. So what we're doing is we're trying to measure what energy we get out when we apply the Hamiltonian to that state. And the lowest energy state is the one, what we're trying to do is find the wave function that gives us the lowest energy, because that's how we found the ground state of a chemical system. But the problem is now we've set the wave function. So when we try to solve this, what exactly are we changing? And for the Hartree-Fock approximation, what we're doing is we're going to change the orbital functions. So our Slater determinant is made up of the orbitals. And what we do is iteratively change these orbitals in a way that will minimize the energy. So that gives us the Hartree-Fock equation, which we try to solve. And we replace so you can see this has a similar format to the Schrödinger equation, but we change the state dependency to the dependency on the number of spin on the spin orbital functions themselves. And we have this new operator that replaces the Hamiltonian, and we call this the Fock operator. So the way that this differs from the Fock, from the normal Hamiltonian is that we still have the kinetic energy term for the electrons, and we have the nuclear charge terms with the interaction between the nuclei and the specific electrons. But then we take away the electron-electron interaction terms and we replace it with something called the Hartree-Fock potential. And what that is a representation of that mean field that we were talking about earlier. So we replace all of the explicit interaction between the different electrons with an average treatment that's comprised of the Coulomb interaction between the different electrons, and then minus the exchange, which reduces the repulsion forces. And this potential is determined by the orbitals themselves. So what we're trying to do essentially is find some orbitals that will give us certain states from the Hartree-Fock equation, and we do that in a diagonalization of the Fock operator itself. But the Fock operator, in order to build it, we need to know like a set of orbitals that we can construct this mean field in the equation. So the way that we solve this Hartree-Fock equation is through something called an SCF cycle, or a self-consistent field cycle. And what this essentially is we try to update the field in a way that the field representing the average interaction of the electrons based on the orbitals, and we do that by changing the orbitals. So if we start off with an initial orbital guess, the cycle is essentially by taking the orbital guess and using those spin orbitals to create that Hartree-Fock potential, which is the approximate electrostatic field. We then use that electrostatic field to complete the Fock operator, and then we solve the Hartree-Fock equation by doing a diagonalization of the Fock operator. What we do after that is we update the spin orbitals using the solution from the Hartree-Fock equation, and then we check if there's a termination criteria that's been satisfied. So what essentially they'll be checking is either that the energy resulting from the solution of the equation is not changing anymore when we went from one cycle to the next. So there's a change less than some threshold that we can specify or is already set, or if the field itself is not changing. So we're changing the spin orbitals, but the field isn't changing. And what that would indicate is that we've now arrived at an optimized set of orbitals. That optimized set of orbitals minimizes the energy of the Hartree-Fock equation. And we would just repeat this process iteratively until we reach that convergence that outputs the orbitals that minimize the energy. So some advantages of this is that it provides us a trade-off between the accuracy and the cost. So what we've done is we've taken the many-body system, the many-electron Schrödinger equation, and we've simplified it to simply be a system where we have a set of one-electron equations. And that greatly reduces the cost of the computation compared to the full configuration interaction method. But that also comes at a cost of the accuracy, because now we're neglecting the specific interactions between all the different electrons at the same time. So even though we've sacrificed that accuracy, the Hartree-Fock approximation can still provide useful answers for certain chemical systems. For example, those that have really weak correlation. But probably the most important reason why we would use Hartree-Fock is that it forms a really good foundation for the application of more advanced methods. So one of the ones that we talk about later on in this lecture is the couple cluster theory, or couple cluster approximation. That and some other higher level theories all build on the Hartree-Fock approximation as their first step. And they use that to form the orbitals that they use in their methods. So Hartree-Fock is really useful. Is really useful for kind of the first stepping stone in our pipeline of solving the electronic structure problem. And the reason why we use it as a stepping stone rather than just the method itself is, like I explained, when we treat the interaction between the electrons as a mean field rather than explicitly accounting for the different correlations, we make this method inaccurate for systems that have strong correlation, because we're neglecting that correlation in our solution. So for most systems that we're really interested in studying, the correlation is difficult to model anyways, and then the Hartree-Fock method neglects this, so it doesn't form an acceptable level of accuracy for our purposes. So just to help you kind of visualize how you would even apply this, if we take a look at some code that would allow us to run a Hartree-Fock calculation on a hydrogen molecule, there's a very useful open source Python library called PySCF. And as you can see, you can do a Hartree-Fock calculation in very few lines of code. And the steps are essentially can be broken into 3 parts. The first part is to specify the chemical system that you want to study. The second part is to create the Hartree-Fock calculation object, and the last part is to run it. So the 2 parts that you need to, as a very basic example, for specifying the chemical system is first you need to be able to specify the geometry of the molecule. And what you're doing is specifying where the nuclei of that specific chemical system are situated in 3D coordinate space. So the way you do that is with the string, where you first specify the atom label and then the 3 X, Y, and Z coordinates. And you do that for each atom. You basically say there's this atom present in the system and it's located at this position. So in this case, for the hydrogen molecule, we have the 2 hydrogen atoms, and the last coordinates of the second hydrogen atom is 0.74. And what that means is there's a distance between the 2 nuclei of 0.74 angstrom. And so now that we know the kind of the positioning in space, we also need to take a look at how we're going to represent the orbitals in the system. So that's where we have to select a basis set for this calculation. So the basis set specifies the functions that are going to be used to describe the atomic orbitals of that atom. And in this case, we're going to use the SDO3G basis, which is the minimal basis in that it uses the minimum number of functions necessary to describe those atomic orbitals. The reason why we use this is because this basis set specifically, not SDO3G, but like the basis set that you use determines the number of orbitals you have in your system. And as I mentioned, the number of orbitals determines some of the computational cost in your wave function. So as you make it more descriptive, you'll be able to get a better solution. But obviously, there's no free lunch, and when you do that, you increase the computational cost and make it harder to solve the problem. So in this case, we're just going to use a really small basis set that doesn't really give like meaningful solutions for big problems, but for this example, it suits our purposes. And then what we do is, now that we have the description of the system in space, and we have the description of the functions that we're going to use to represent the orbitals, we can create the molecule object from those 2 pieces of information. And then next, we set up the Hartree-Fock calculation. And it's very simple. You just provide the molecule object that you just created to the RHF function, and it returns a restricted Hartree-Fock object. And then we just run the calculation. And when you run with the .kernel or .run, what that does is it will run the SCF cycles until the energy is converged. And at that, so what it does is every iteration, it changes the orbitals until either the energy or the orbitals no longer change. And we have an example of the kind of output from this Hartree-Fock function on the right. So for the hydrogen molecule, when you run Hartree-Fock, the energy that it returns is minus 1.1167 Hartree. So that leads us into an example of the full CI method. So earlier, I described the full CI method before talking about Hartree-Fock, but the reason why I put the code afterwards is because in PySCF, in order to run the full CI calculation, you need to have a description of the orbitals that you're going to use. And when we run the Hartree-Fock calculation, it outputs the optimized orbitals at the end. And in this case, we just use those as the orbitals for the full CI calculation. So we have the same steps where we specify the system and the basis set, we create the molecule object, and then run a Hartree-Fock calculation. But then when you do the full CI method, we simply create a full CI object with the molecule and then the optimized orbitals from the Hartree-Fock calculation, and then we run the full CI calculation with the dot kernel method. So what that returns is an energy and a wave function. So the energy FCI represents the exact energy for this system in the basis set that we chose. And what the CI represents is the wave function. So for full CI, which is full configuration interaction, we consider all of the possible configurations in our wave function. And that is basically just the linear sum of those Slater determinants, but it's every possible valid Slater determinant for the system. And they have the coefficients in the wave function have all been set in the diagonalization, because those Slater determinants form the basis state, the states in the basis of the Hamiltonian. And when you do the diagonalization, it outputs the eigenvector for the lowest eigenvalue, which represents our ground state. The eigenvector represents the ground state, and the values in the eigenvector are the coefficients in the wave function. So if we see on the right the output, we have first the Hartree-Fock output from the Hartree-Fock calculation, and then we have the FCI output, which is minus 1.137. And what that shows is that we have this deficiency where Hartree-Fock is not able to capture some of the correlation in the system, and that's why the full CI energy is lower. So that difference kind of leads us into why we would need to use another method on top of Hartree-Fock, because we're trying to capture that correlation energy and have it be included, because we're trying to get accurate descriptions of these states in our system. And that leads us into the one very common and widely used method that's built on top of Hartree-Fock, which is the coupled cluster approximation, or coupled cluster theory. So like we just said, Hartree-Fock, we need to be able to model the electron correlation in the system. It's really important, and it's crucial for calculating the molecular properties and energies, but Hartree-Fock itself lacks that correlation because of the mean field approximation that we used, where we described the electron-electron correlation using just an average. So we know that we want to capture correlation, but we don't have, but also full CI is too expensive to use. So we start looking at other ways of approximating this correlation without having to take into maybe account all of it, or just another way that will reduce the computational cost. So the first thing to consider is that there's an approximation called the independent electron pair approximation, which is where we try to describe the correlation between two electrons specifically, and we just focus on those two electrons, and we neglect everything else in the system. We just don't think about it. We treat it as being independent to that pair that we're considering. But now that's not very accurate, and there's some issues with it. So the next step of this is called the coupled cluster approximation. And now what this does is that it accounts for the correlation between pairs, but between all pairs, and also not just pairs, but higher order groupings. And what we try to do is include correlation in our wave function by using this approximation. So the way that it works is that we will describe our wave function using an exponential ansatz. So we have this is our wave function psi. That's the exponential ansatz ET applied to our reference wave function. And as I mentioned, coupled cluster theory is a post-Hartree-Fock method. So it builds on the results of Hartree-Fock. And we use the Hartree-Fock wave function as the reference in the coupled cluster theory. So at that point, it's just the Hartree-Fock Slater determinant, but it's represented in terms of the optimized orbitals as the spin functions. So then we have this form of our ansatz, and the T in the ansatz is the cluster operator, which is T, and then it's the sum of T1, T2, up to however number of possible excitations we have, which is like Tn. If we have n electrons in the system, we could move all of them around. And what these cluster operator represents is all the summation of all the different possible ways of pairing these electrons. So rather than just considering only one electron and having everything else be treated in an average way, or compared to the independent electron pair approximation where we just consider a single pair, the couple cluster approximation considers single electrons moving around and considers pairs and triples and quadruples, and we can kind of start to approach the full configuration interaction wave function by increasing higher order groupings. And these specific operators are defined in terms of what are called fermionic annihilation and creation operators. So we are looking at everything through the formalism of something called the second quantization. So it's a way of describing the electronic structure problem, focusing on orbital occupancy and whether or not there's an electron in a specific orbital. And what these annihilation and creation operators do is move particles around. So if we apply a annihilation operator to an orbital that is occupied with an electron, then we will now take that electron out of that orbital. And if we apply the creation operator to an unoccupied orbital, it will be the same as placing an electron there. And these operators satisfy the same anti-symmetric relations that we need for our wave functions. So when we take a look at these terms that make up the cluster operator, they're actually operators that create excitations. So it's a sum of excitations. So for T1, it's a single excitation. And what that is a way of moving one electron from an occupied orbital to an unoccupied orbital. And that's why we have this creation operator at orbital I and the annihilation at orbital A. And we have these coefficients TIA, which are the amplitudes in the wave function. And the single excitation operator is the sum of all possible single excitations that we can create. And in this wave function, it'll be the single excitations applied to the Hartree-Fock state. Then we have T2, which is the double excitations. And the double excitations have essentially pairs of electrons moving. So rather than just moving a single electron from an orbital to another orbital, we're moving pairs of electrons around. And we still have the same amplitudes. And what we do when we apply this method is we have the excitations defined in our ansatz, and we have to solve for the amplitudes. And the way that we do this is that we have a set of coupled equations that are created from the ansatz and the Hamiltonian. And what we do is we project that onto the state created from each excitation level. So we would go from 0, where we have no excitations. That's one possible thing. It's the Hartree-Fock state. And we use this equation to evaluate the energy. Then we have the next one, which is with a single excitation. So we replace phi 0 with maybe phi 1. Then we have the doubles, which is phi 2, and that goes all the way up to phi star, which is the highest level excitation that we're considering. And we solve these equations, that not the Hartree-Fock one. We solve the ones with all the higher level excitations to provide the solutions for the amplitudes in the wave function. And this solution gives us a correlated wave function that solves the Schrödinger equation. And unlike Hartree-Fock, it includes correlation between the different electrons because of the fact that we're considering moving them around together and we're taking into account the different effects that they have at different levels. But so as I said, the number of like excitation ranks that you have in your cluster operator can go up to the number of electrons that you have in your system. And that starts sounding a lot like full CI, where we're trying to keep track of all the different ways that we can move electrons around. And that scales exponentially because of the way that we choose how many times we can move electrons around and how many possible ways. So we have to typically perform a truncation where we only consider the excitations up to a certain level. So maybe you could say, I want to consider only up to singles and doubles, and I'm going to neglect everything higher order than that. So if we don't do that, we don't truncate. When we solve those equations and we get the amplitudes, we get that state that was created from the wave function with the amplitudes in it, that forms an exact solution to the Schrödinger equation. But like I said, with full CI, it's extremely costly to consider all these different excitation levels, and it's not actually feasible to do on systems that are of any relevance. So what we typically do is we perform a truncation and we consider only all the excitations up to a certain level. So very commonly, people will use CCSD, which is a couple cluster theory with singles and doubles. And that's where we specify that the cluster operator is comprised of all the single excitations and all the double excitations. And then this, unfortunately, isn't enough for very strongly correlated systems that are bigger and or that are more complex. So if we use the CCSDT, where we include also triple excitations, generally you can get a good answer with that, but it's very expensive to do. And obviously also it's not a good answer for every possible system you can use. There are systems that have a lot of correlation of lots of different types of electron numberings, and performing a truncation at the triples, you still sacrifice some correlation. So there's always a give and a take, and we're trying to find the level that provides us with satisfactory accuracy. But a nice thing about the couple cluster ansatz, where we have the exponential ansatz, is that even though we perform a truncation to a certain level, so let's say we consider the case on the left where we truncate to singles and doubles only, because of the format of the ansatz, we can still capture some higher order excitations. So if we expand the ansatz as a Taylor series, you can see that we don't only have the single and doubles, we also have interaction between them. And that can give us higher order determinants in our wave function. Because like one example would be, if you have your Hartree-Fock state and you move one electron out of that state into like another unoccupied orbital, then that's a singly excited state. Then if you move the double from there, you could move two electrons that were still in the Hartree-Fock state and move them to two other unoccupied orbitals. Now we have three electrons that have been excited out of the typical Hartree-Fock reference into different positions, and that forms a triply excited state. So thanks to this, even though we perform the truncation, there's still the possibility of capturing some higher order excitations in our wave function. So some advantages of using the couple cluster approximation is that it gives us an accurate solution at certain levels. So you have to pick what level of excitations you're going to consider. One setting that's typically used is CCSD with perturbative triples. So we don't consider all the triple excitations in the typical way. You use perturbation theory to take into account some of the triples in your wave function, and it can give you more accuracy than CCSD with lower cost than CCSDT. But this, for certain systems, you might need to include more excitations. If you start doing things like bond breaking, you might need to have higher level excitations, and that's when it can start to get costly. But another benefit of using couple cluster theory is that it's size consistent. So this is an important property for computational chemistry methods, and it's essentially that the energy of a system of two components that are considered together must be equal to the energy of the system A and plus the energy of the system B. So if we have, for example, two molecules and they're far apart, we individually solve for the energy of each one. It should be the same as considering them together. It's like it should be the two energies added together, and that's an important property, and it's one that couple cluster theory satisfies. Another advantage is that, unlike Hartree-Fock, it systematically includes electron correlation in the wave function. We do that systematically through our construction of the cluster operator. Unfortunately, it does have some disadvantages. So I'll start with the one on the right. It's computationally expensive for larger systems. If you're trying to consider large complex systems with various like types of reactions that you're trying to take into consideration, you can end up having to include a lot of excitations in the ansatz, and that leads to a lot of coupled equations that have to be solved, and it really increases the computational cost a lot. Another disadvantage is that due to the non-linearity of the ansatz and the fact that we're solving those those couple cluster equations, and we're not trying to actually minimize an energy, we're just trying to solve the equations, the method isn't variational. So the result of that is that the energy isn't lower, the energy that we get out of with our solution isn't lower bounded by the true energy of the system. So if we're looking for the ground state, the energy that we get out when we try to find the ground state with a couple cluster method is not lower bounded by the true ground state energy. And the reason why that's important is that if you're performing these simulations on a system that you don't know the true answer for, like the experimental results or something like that, you don't know if you can trust the result or not. You don't know if it's overestimated energy, underestimated energy, and an example would be like CCSD can sometimes overestimate the correlation energy up to like 120%. And all of a sudden you have an energy that if you trusted it, you would have an unphysical state. So it's a bit of a problem with CCSD or couple cluster theory in general. But so an example of how you can run a CCSD calculation with PySCF, it has the same steps. You'll see it's a common trend. In order to simulate a chemical system, you have to specify that system. So we do have the geometry. You have to specify the basis set so that we know how we can describe the orbitals. And then very often well, not very often, in all cases where you're doing a post-Hartree-Fock calculation, you have to run a Hartree-Fock calculation first. And then we use that as the building block for the application of our more advanced methods. So in this case, we would be able to just use the CC or couple cluster module and create a CCSD object by passing in that Hartree-Fock, the Hartree-Fock object after performing the SCF optimization. And then we just run the calculation. So it's very simple, but the output on the right, so once again, every time we run a Hartree-Fock calculation, unless you change PySCF's print levels, it will print out this converged SCF energy. It tells you that the calculation converged and that the energy is this. And then when we run CCSD, we get out the output energy and also gives us the correlation energy. So as you can see, when we apply CCSD on top of Hartree-Fock, we can recapture some of that correlation compared to Hartree-Fock. So we see that Hartree-Fock was minus 1.116 and CCSD is minus 1.1372. Then if I go back to full CI, you can see that the CCSD is within like a meaningful level of accuracy to that. It's accurate up to like at least the 4th decimal place. So for a small system like H2, which is not very complex, CCSD is very good. But obviously the problem comes in when you're trying to apply this to a really large system and you need to take into account lots of excitations. It gets very expensive. So that takes us to the last method that we're going to consider in today's lecture. And this is selected configuration interaction. So it has it basically builds off of the full configuration interaction method and is another way of trying to reduce the computational cost of FCI. So the reason why we consider this, as I said, FCI is infeasible for the systems that we really want to study because of the exponential scaling. But what SCI does is it tries to retain chemical accuracy. So that's just a certain threshold of accuracy in our answers that people will use as an acceptable level. We try to retain that level of accuracy, but we use only a subset of the configurations in our wave function. So full CI has all of the possible configurations, and we try to use only a subset of that in SCI. So the reason why we can do this is that it's actually the case that if you're looking for a ground state, that the ground state is sparse. What that means is that if we consider the full configuration interaction wave function, which is over here, it's the linear sum of all the possible different Slater determinants. Actually, the number of Slater determinants that have CI values that are significant and they significantly contribute to the energy of that state is relatively low compared to the size of the space. So we have an exponentially scaling space, and the scaling of the number of Slater determinants that are relevant or really important for capturing a lot of the correlation doesn't scale exponentially. So what we can then do is try to find those Slater determinants or those configurations. and just extract only the set that we need in order to retain a certain level of accuracy. Obviously, if you change that threshold, you need more states, and you need to expand your SCI, and that expands the cost of the method. But in general, what we're going to be doing is performing a search for these specific determinants. So what we do in SCI is that we perform different iterations, and in each iteration we try to generate configurations that are going to go into our wave function, and we rank those configurations or determinants based on the contribution of their energy to the wave function. So we have our wave function, the SCI wave functions of this format, and in order to evaluate the energy of this, what we do is we take our Hamiltonian matrix and we project it into the space spanned by these determinants, because these determinants form basis states of the Hamiltonian itself, and we can reduce the dimension of the Hamiltonian by projecting it into this reduced subspace of orthonormal states. What we then do is we perform a diagonalization of that reduced matrix, and that outputs the solutions from the SCI, the solutions to the Schrödinger equation for that subspace Hamiltonian. Also, it gives us the exact coefficients in the SCI wave function for the states that we used. And you can then use that to perform like an update step, where you then try to find more configurations that can contribute to your wave function, or you take out ones that don't contribute. And there's also ways to do this without having to explicitly diagonalize your Hamiltonian. So there's been a lot of work. So there's some methods like heat bath configuration interaction and adaptive configuration interaction, adapted selected configuration interaction, so ASCI. And they all have different methods of trying to build this compressed wave function, but they all have kind of the same core purpose, which is to search through the space of all the possible configurations and try to extract the ones that are the highest contributors to our energies. And because the search space is so large, the search has to be intelligent. Yeah, so that leads us to the conclusion of our talk, which is simply to discuss some of the advantages and disadvantages of SCI. So like I said, we consider SCI because the FCI, full configuration interaction method, is too expensive to use, and SCI is much more computationally efficient than FCI. I talk about using a subset of the configurations in our wave function, but we don't start off with a big wave function. We iteratively build it up from a low number of configurations. So we always have control over how big is our wave function, how much memory are we using, what are the computational resources of doing this diagonalization, stuff like that. So we can control how much resources we're using at the expense of accuracy. So there's also a consideration of needing to increase resources if you need more accuracy. But SCI can generate very accurate solutions for certain systems. But the problem is that unlike the couple cluster theory, SCI isn't size consistent. The reason it's not size consistent is because we're performing a truncation of the configurations, and then we're only considering configurations up to that level. So yeah, it's not size consistent, but it is more efficient to do than FCI. And that kind of brings us to the end of today's lecture. So what we did as a summary was we covered the exact method of solving the Schrödinger equation, and then we covered 3 different methods for trying to obtain good answers or accurate solutions without incurring the cost of the exact solution. That was our Hartree-Fock approximation, the couple cluster approximation, and selected configuration interaction. And the purpose of this was to just take you through what are the normal methods that someone might be using in the normal classical methods in trying to solve this electronic structure problem. So that next week, when we talk about how can you use quantum computers to solve this problem, you have some understanding of why we would want to use a quantum computer versus a classical computer, or why you might want to do that. And yeah, that's everything for today. Thank you.
Okay, thank you, Shane, for the lecture. Do we have any questions from the online participants? If you want to raise your hand, please feel free to do so, or just type into the Q&A, and we can get around to answering your question. I see we have like one question in the chat from Eugene. So he says, how does density functional theory compare with these methods?
Okay, yeah, so that's a great question. So density functional theory takes a different approach to the methods that I mentioned. So today, the methods that we covered are considered wave function methods. So what we're doing is we're trying to solve the Schrödinger equation and get solutions in the form of a wave function. But like we say, you incur a lot of cost when you do that. And what the density functional theory does instead is they say that you can form the energy as a functional of the electron density of your system. So we have some functionals that we can use of the density, which describe the distribution of electrons in our system. And rather than having to explicitly solve the Schrödinger equation, we can simply try to solve an energy equation of those densities. And you don't have to consider the wave functions themselves. So it's a very commonly used method. In fact, I think quite a significant proportion of supercomputer resources globally are used to run DFT calculations. I think in the UK, one of the main supercomputer facilities, something like 45% of their yearly usage is on DFT calculations. People use them a lot because it's cheap. It's less computationally expensive than even Hartree-Fock, but it can have problems describing certain mechanisms like intermolecular interactions and things like that. So the reason we didn't cover it today is because when we talk about quantum computing for the electronic structure problem, we're talking about a wave function method, and the DFT differs from that as being a method that focuses on the electron density. An interesting thing about density functional theory is that we know that there's an existence of a function of the electron density that will give us the exact solution, but we don't know what that functional exactly is. So we use approximations for it. But there's also some interesting work that's been done in machine learning and AI to try to make AI generated functionals that are used in that. So yeah, so DFT is not a wave function method, and that's how it differs from the ones that we discussed today.
Okay, thank you for that. So are there any Okay, one sec, we just have a question from a participant.
It's myself. Okay, thank you very much. I have a quick question about, you mentioned along with the energy, in one of the slides you mentioned electron correlation as well. Yeah, that one. Yeah, that one. You just, yeah. No. The other one that you just. I'm just talking about the CCSD. Yeah. Not just energy correlation. Yeah. This is an electron correlation between these two H molecules.
Yes. So,
and does it have any specific unit or?
Yeah, it's in Hartree. So it's defined.
Correlation also is.
Yeah. So it's defined in terms of the it's the difference in. Okay, so the definition of the correlation energy is the difference between your Hartree-Fock energy and the exact solution. So because Hartree-Fock neglects that correlation, the explicit correlation between electrons, we try to regain that, and we call it the correlation energy. And the unit is Hartree, the same.
It's the energy.
Yeah, it's the energy. So it's basically, in this case, it would be the difference between the CCSD energy and the Hartree-Fock SCF energy, which is minus 0.02 Hartree.
That's correct.
Yeah.
But in general, is it in this specific case or in general?
In general. So if you said that we're trying to capture some correlation energy, you would measure it in terms of the Hartree in the same units as the energy itself, because it is an energy value.
Okay. And the other question is, you consider a specific distance here, right?
Yes.
Okay, 0.47 angstrom. Okay, but it's not necessarily the equilibrium. We need a for loop or something.
Yeah, so exactly. So what you would do is, I think that, let me just open this up. There is a, remember, sorry, I can't change my screen sharing easily, but remember in the last lecture, there was a plot where we were talking about how in the Born-Oppenheimer approximation, you set the nuclei to be set, we treat them as a field of point charges, and then we consider electron motion. And then you try to introduce the motion of the nuclei through the geometry. So that would be, at this point, where you change the geometry to give different distances between the atoms, and you would have to solve that at the different distances, and then that would give you your potential energy surface, which describes the motion of the nuclei. So, like you said, I don't know if this, I can't remember if this is the equilibrium distance, but you'd be able to do it by changing the bond length, and then you would see the points on the potential energy surface that had the lowest energy would be your equilibrium points.
Okay, and what if we have more than 2 atoms, like 3 atoms? So what's the trick?
So you'd have to pick which one you're stretching. So you could do it symmetrically or asymmetrically. So for example, if you had like a water molecule, you have 2 OH bonds, and you can choose to stretch either only one OH bond, or you can stretch both of them. You can do them at the same amount of stretch, or you can change that. So I'm not exactly sure what if there's a general rule on how you would change the system. I think it'll depend on what the application is. But
and if we change it at the same time, the curve
will
like
change.
3D.
So
more complicated.
So what you try to do is get the simulation to agree with the experimentation. So very often when people are applying certain methods, they'll have some experimental data, some curves that they've gotten and from specific energies, and we just try to match the curve. And there's people with computational chemistry backgrounds will know how to change that the system for that.
And my last question is, should we necessarily run first the Hartree-Fock and then the post-Hartree-Fock method, or
it's because, so the reason why you'd want to run Hartree-Fock to use as your reference for another method is that the Hartree-Fock state has the lowest energy out of any single determinant wave function. So it forms a really good starting point.
I mean, if you just remove those lines, those 2 lines, will your energy of the CCSD will change, or?
I think it would change. I don't know if it's even supported in PySCF to do that. I know you have to give it, you have to give it a
educated guess.
An educated guess. And the reason for that is, if I just try to get this to change. So the wave function is defined with respect to some reference state. So you need the reference state.
0 cannot be anything arbitrary.
And if you had this as a multi-reference starting point, so like instead of having a wave function with just one determinant, you had multiple determinants, it increases the complexity of your solution, your solving process. So if you use just Hartree-Fock, it's the lowest energy single determinant wave function, and it's a really good starting point for coupled cluster theory.
And this size 0 for Hartree-Fock method, what is that one?
So that one is so it's just the one determinant. The one determinant here, and the Hartree-Fock state is where you populate the lowest energy orbitals. So
all electrons
in the lower energy orbitals.
Singlet.
So, exactly. If it's a closed shell.
We can have open shell.
So if you have open shell, you can have unpaired electrons, and that changes the state. So if you have we have alpha and beta electrons, and you can have cases where we have more alpha electrons than beta, or the other way around. It changes the state that we're looking for. So if we have all the electrons are paired, the state is the ground state is a singlet state, and if you have one unpaired electron, then the ground state is a doublet.
So it's like a in chemistry, people call it the radical.
Yeah, exactly. Yeah.
It's not close. Okay, thank you so much. Yeah.
Okay, I think there's just one more question from Cyprian. So their question is, could you elaborate on why density functional theory methods are particularly not useful for intermolecular interactions? Which specific methods, wave function methods, would you recommend for describing intermolecular interactions?
So I'm not super knowledgeable about DFT, which is why I didn't really include it, especially since it's not a wave function method. But to my knowledge, it depends on the way that the correlation functionals in DFT work. So it has some problems with specifically with those cases as a result of the approximations that we use. I don't know more to answer the question, but I do know that on the Wikipedia page, you can find some like summarized descriptions of this, which I think would be useful if you wanted to find out more about that. And then with regards to the second question about which wave function methods to use, I'm not sure about that either. It seems that all of them have some give and take. So there's all the different methods, they have some advantage, some disadvantage, and there's never one that really does everything that you would want to do, which is why it's still like an open field of advancements and improvements in these methods.
Okay, since it's 3, I think we can finish up there. So thank you, Shane, again for the lecture. And there's another one next week. So there's 2 more remaining. Okay, so hopefully see everybody next week at the same time. Thanks.